Europe and Africa are separated by only about 14 kilometers at their closest point, but a direct route near that narrowest point would cross water more than 800 meters deep. So engineers have studied a longer path, one that avoids the deepest channel, but enters fractured, water-bearing ground beneath the Strait of Gibraltar. To connect these continents, they would not simply have to tunnel beneath the sea. They would have to find a route the geology would allow them to build. From southern Spain, the coast of North Africa can appear almost close enough to touch. Cargo ships and ferries move through the water, connecting the Atlantic Ocean with the Mediterranean Sea. Far beneath them, a hypothetical railway could carry passengers and freight directly between Europe and Africa, but this tunnel does not exist. Spain and Morocco have studied a fixed link for decades. Yet the official material examined for this documentary describes continuing investigation and technical development, not an approved full construction program. Every completed tunnel, terminal, and railway shown here is a concept visualization. A real system would require approach railways, portals, terminals, electrical power, ventilation, drainage, and a shared emergency network. The tunnel would be the centerpiece, but it would only work if every surrounding system worked with it. Today, the rail systems of Europe and North Africa remain physically separated by the Strait of Gibraltar. A train cannot continue directly from one continent to the other. Passengers, vehicles, and freight must transfer through ports, ferries, or other transport systems. A fixed railway link would attempt to remove that physical break in the corridor. Passenger and freight trains could potentially continue beneath the strait without changing transport modes at the coast. But removing the break would only create value if the terminals, border systems, and connecting railways could handle enough traffic to justify the tunnel. It would not eliminate shipping. It would not automatically make every journey faster. And it would not justify its own cost, simply because the two continents are close together. Before economists could test the business case, engineers would first have to prove that a buildable route existed at all. The obvious starting point is the shortest line across the water. At the narrowest part of the strait, Europe and Africa are separated by approximately 14 kilometers. But surface distance is only one part of tunnel geometry. Near that direct route, the seabed drops beneath extremely deep water. The tunnel would have to pass below the seabed while preserving enough geological cover to maintain stability and reduce the risk of opening a direct hydraulic path toward the sea. A railway cannot simply dive toward the center of the strait and climb back toward the surface. Heavy trains require gradual gradients. The deeper the central tunnel becomes, the farther the approaches must extend beneath the land. That can turn a short sea crossing into a much longer underground railway. Studies therefore moved farther west toward the Camarinal sill. The studied marine corridor is approximately 28 kilometers long, but its maximum water depth is around 300 meters, far shallower than the direct route near the narrowest part of the strait. That solves one problem by creating several others. A longer tunnel means more excavation, more lining, more ventilation, and longer emergency routes. It also exposes the machines to more ground that may change unexpectedly. So the best route is not simply the shortest. It is the route where water depth, ground conditions, railway gradients, and safety systems can all be made to work together. The completed tunnel would be protected from most surface weather. Construction would not. Survey vessels, drilling equipment, and marine logistics would have to operate around waves, changing winds, and an internationally managed shipping corridor. Vessel movements through the strait are monitored through reporting centers in Tarifa and Tangier. Any major investigation campaign would have to coordinate with active maritime traffic, rather than treating the surface as an empty construction zone. The land sites would be just as important. Each portal area would need space for launch chambers, concrete segment production, material storage, spoil handling, electrical supply, workshops, and years of construction traffic. The approach railways would need gradual alignments, long enough to reach the final tunnel elevation. A route could be suitable underground and still fail, because the surface logistics did not work. The buildable alignment must therefore connect three things at once: acceptable geology, practical portal sites, and functioning railway approaches. Before engineers can choose that alignment, they must investigate a landscape hidden beneath hundreds of meters of water and sediment. Sonar can map the shape of the seabed. Sub-bottom profiling can reveal shallow geological layers. Sediment samples and rock dredging can show what lies at selected points. Drilling can recover deeper cores, but each core represents only one narrow column of ground. Between those columns, engineers must interpret how rock layers, faults, and ancient channels continue through the strait. An official agreement published in late 2025 called for additional investigation around the Camarinal sill. The planned work included multi-beam bathymetry, seabed reflectivity, sub-bottom profiling, sediment sampling, rock dredging, laboratory analysis, and integration into a three-dimensional geological model. The ground is not completely unknown. Decades of study already exist, but no practical survey can physically inspect every meter of a long subsea alignment. The first megaproject is therefore not excavation. It is reducing uncertainty enough to decide where excavation can safely begin. Much of the studied corridor passes through formations described as flyash. Flyash is not one uniform block of strong rock. It can contain alternating layers with different strength, stiffness, and permeability. A tunnel boring machine could advance predictably through one section, then enter material that responds in a completely different way. The most difficult areas may include ancient channels filled with breccia. Some sampled breccias contain rock fragments inside a clay-rich matrix. In the studied Gibraltar conditions, these zones may be saturated and capable of deforming under high stress. Once excavation removes the support previously provided by the ground itself, the material can squeeze inward. That does not necessarily mean a sudden collapse. It means the tunnel boundary continues moving toward the opening. Even moderate movement can increase friction around a tunnel boring machine shield, overload support systems, and restrict the space required for the machine to advance. Technical work examining the Gibraltar case identifies the breccia-filled paleo channels and the risk of heavy squeezing as central challenges. The concern is not only face stability, it is also shield loading, excessive deformation, and the possibility of trapping the machine deep beneath the strait. A machine powerful enough to cut hard rock is not automatically a machine capable of surviving deformable ground. The project-breaking risk is not simply weak material. It is encountering pressurized ground that deforms faster than engineers can stabilize it, interrupting the only practical excavation path beneath the sea. The real task is controlling how the ground reacts after it has been opened. The published baseline concept does not place two tracks inside one large tunnel. It uses two separate railway tubes, each carrying one track, with a smaller service and safety gallery between them. Cross passages connect the three spaces. Under normal operation, trains would use the running tunnels, while the central gallery supported access, maintenance, and emergency movement. If one running tunnel became unsafe, people could move through protected passages into a space separated from the incident. Published study parameters include nearly 28 kilometers of subsea tunnel and a railway gradient of approximately 3%. These are study figures, not final construction dimensions. Updated geology, safety analysis, and railway requirements could change them, but the basic concept reveals an important principle. The empty tunnel reserved for safety could be almost as important as the tunnels carrying trains. Construction would begin on land. On both continents, crews would establish access routes, power systems, workshops, spoil handling facilities, and portal sites. Large underground launch spaces might be required to assemble the tunneling machines near the final railway elevation. Excavation would first create the portals and launch chambers. Concrete segment production, material storage, and muck removal systems would need to operate continuously for years. The approach works would also contain the future railway, drainage, ventilation, and emergency infrastructure. Each tunnel boring machine would arrive in sections. Inside the launch chamber, crews would assemble the cutter head, shield, thrust system, and backup equipment. As the cutter head rotated, excavated material would move through the machine and toward the surface. Hydraulic cylinders would push the shield forward against the last completed lining ring. Once the machine advanced, equipment behind the shield would assemble precast concrete segments into a new structural ring. Gaskets would seal the joints. Grout would fill the space between the new lining and the surrounding ground. Then the cycle would repeat. Cut, remove, advance, line, seal. In predictable conditions, tunnel excavation becomes an industrial production process. That rhythm could break down when the ground changes. Probe drilling ahead of the face could identify unexpected water flow, pressure, or weaker material. Engineers might slow the machine, modify face support, inject grout ahead of the excavation, or reinforce selected zones before the cutter head reached them. The construction method would have to respond to the actual ground encountered. No single tunnel boring machine setting would remain correct for the entire route. The smaller central gallery might also provide geological information or access ahead of the larger railway tunnels, depending on the final construction sequence. This remains a possible strategy, not a locked plan. Excavation could progress from Spain and Morocco toward a carefully selected meeting zone. The location of the breakthrough would depend on geology and machine access, not simply the mathematical midpoint. Once the underground space is connected, crews would still need to construct cross passages, drainage, pumping, ventilation, electrical distribution, communications, track, signaling, and emergency systems. The excavation would create the space. Only the systems installed afterward would turn that space into a railway. Most of the individual technologies required for this project already exist. Mechanized tunnel boring, precast segmental lining, waterproof gaskets, probe drilling, grouting, pumping, ventilation, cross passages, and automated railway control are established engineering systems. The channel tunnel already operates with 2 railway tubes and a separate service tunnel. Major base tunnel projects also use large tunnel boring machines, precast lining, exploratory tunnels, and extensive emergency infrastructure. These are proven technologies. The project-specific adaptations are less certain. A Gibraltar tunnel would need boring machines, face support strategies, waterproofing and structural linings, designed for the actual pressure and ground conditions found along the selected route. Those systems are based on existing engineering, but they would require new testing, detailed design, and site-specific validation. The hypothetical elements are more fundamental. The final alignment has not been locked. The exact tunnel diameters have not been locked. The boring machine configuration, construction sequence, portal arrangement, and method for crossing the most deformable breccia zones have not been locked. The machines are real. The construction principles are real. But the final combination remains hypothetical. The sea would not need a large visible crack to threaten the excavation. Water can move through pores, joints, fractured zones, and poorly sealed connections. The first defense would be a stable alignment with adequate geological cover. During excavation, controlled pressure at the tunnel face could help limit ground movement and water entry. Behind the machine, the segmental concrete lining would create the permanent structural shell. Gaskets, grout, and carefully controlled construction tolerances would form multiple barriers. But a long subsea tunnel should not depend on the assumption that absolutely no water will ever enter. Minor leakage would need to flow into drainage channels and sumps. Pumps would remove it. Backup pumps and emergency electrical power would remain available if the primary equipment failed. Sensors would monitor leakage, pressure, deformation, and lining movement. The engineering objective would not be to pretend the water was absent. It would be to control every credible path through which it might enter. A railway tunnel beneath the strait would also have to survive an emergency far from either portal. A stopped train, electrical fault, or cargo fire could produce smoke deep inside the system. Train control would first prevent additional traffic from entering the affected section. Ventilation would then help manage smoke movement and protect the intended escape route. People could leave the train, follow the emergency walkway, and pass through fire-resistant doors into the central safety gallery. The parallel running tunnel might support rescue access, but only after train movements and smoke migration were controlled. Every fan, door, detector, and operating rule would need to behave as part of one response. Concrete alone cannot manage an emergency. The railway would be safe only if its detection, communication, ventilation, and evacuation systems acted faster than the incident could spread. Imagine a freight train leaving Spain. It enters the tunnel under one operating authority, crosses an international boundary underground, and later joins a Moroccan network. For that journey to remain continuous, signaling, train control, braking requirements, electrical strategy, and loading clearances must all be compatible. The terminals would also need to process passengers, freight, customs, and border security without allowing queues to block the railway. Maintenance standards would need to match on both sides. Replacement equipment would need to remain available for decades. And during an emergency, Spanish and Moroccan teams could not wait to debate jurisdiction before acting. A shared operating structure would need to identify the incident, stop traffic, coordinate ventilation, and direct the response from both continents. Spain and Morocco already have a bilateral framework for studying the fixed link. Building and operating it would require a much deeper commitment. The tunnel would not be held together only by concrete and steel. It would also be held together by agreements. A deep tunnel would avoid placing bridge towers and foundations inside the shipping channel, but it would not eliminate environmental effects. Survey vessels create noise. Seabed sampling disturbs selected locations. Portals and work sites affect the coast. Excavated material must be processed, reused, or transported. Even the survey campaign requires environmental coordination. Official planning identifies a special area of conservation in the Western Strait and an area covered by an orca conservation framework. That means environmental review begins before a tunnel boring machine is assembled. A route might appear favorable in geological terms and still require modification because of its coastal footprint or marine effects. The strait is not empty space between two continents. It is a working maritime passage and a living ecosystem. A tunnel can be technically conceivable without being financially ready to build. No validated official budget or full construction schedule exists for the complete fixed link. Any estimate must therefore be conditional, based on the published scale of the Gibraltar concept, and broad comparisons with major railway tunnels such as the Channel Tunnel and the Brenner Base Tunnel. A cautious editorial planning range belongs in the tens of billions of euros. For a core fixed link containing the three tunnels, portals, essential terminals, railway systems, ventilation, pumping, and a realistic geological contingency, an editorial order of magnitude range would be approximately 20 to 30 billion euros. A complete international transport system, including larger terminals, border facilities, connecting railway upgrades, environmental mitigation, and a wider risk reserve, could reach approximately 30 to 45 billion euros. Severe geological problems could push the cost higher. This is not an official project estimate. It is a conditional editorial range based on comparable infrastructure and the known scope of the studied concept. The schedule would carry the same uncertainty. Detailed investigation, design, environmental review, and international approvals could require approximately 4 to 7 years. Portal works, launch chambers, and main excavation might require another 7 to 10 years. Railway installation, ventilation, testing, emergency exercises, and commissioning could require 2 to 4 more years, although some of that work could overlap with the final stages of excavation. That produces a conditional total of approximately 15 to 20 years, from advanced investigation to operation. In an adverse geology scenario, the program could extend beyond 20 years. The greatest uncertainty is not the amount of concrete, it is the time and treatment required to cross the weakest ground. And once the fixed link opened, it would still require enough traffic to support continuous inspection, staffing, energy consumption, and replacement of safety-critical equipment. The project would have to prove two different things: that engineers could build it, and that enough passengers and freight would use it to justify maintaining it safely for generations. So, could we build a tunnel between Europe and Africa using a 6-part editorial assessment? The answer is technically promising, but far from certain. For technology, the project scores 15 out of 20. Long railway tunnels, mechanized excavation, segmental lining, ventilation, and automated control already exist. The difficulty lies in adapting and combining them under this specific mix of depth, distance, and variable ground. For geology and water control, the project scores 8 out of 20. The route has been studied, but breccia-filled channels, squeezing behavior, and limited subsea access remain the largest technical uncertainties. For safety and operations, the project scores 12 out of 20. Separate running tubes and a central safety gallery create a credible foundation for evacuation and rescue. Long distances beneath the sea still make smoke control and emergency access difficult. For environmental compatibility, the project scores 11 out of 20. A tunnel avoids large offshore bridge structures, but surveys, portals, construction logistics, and long-term energy use still require careful review. For economics and demand, the project scores 7 out of 20. There is no validated official cost, financing package, or proven full system demand case. For international cooperation, the project scores 12 out of 20. Spain and Morocco have maintained a long-running study framework. Construction and operation would require a stronger shared institution capable of surviving political, financial, and technical change. The total is 65 out of 120. Converted to a 100-point scale, the score is 54 out of 100. This is an editorial engineering assessment, not an official project score. Using existing tunneling technology, the fixed link appears technically conceivable, but without a validated route through the weakest ground, an official cost and schedule, and a proven operating agreement between both countries, it is not construction ready. Europe and Africa are close enough to see across the water, but that visible distance hides a much larger engineering distance beneath the surface. A buildable tunnel would have to negotiate depth, squeezing ground, water pressure, railway gradients, emergency access, environmental protection, and 2 national operating systems. Building it would require more than a powerful machine. It would require survey teams to understand the same hidden ground, construction crews to work toward one another from 2 continents, operators to trust the same control system, emergency teams to follow the same plan, and 2 countries to maintain the same railway for generations. The greatest achievement would not be forcing the shortest possible line beneath the strait. It would be learning enough about the ground to know where that line should move, and how to protect every train, worker, and passenger after excavation began. The distance between Europe and Africa can be measured in kilometers, but the real distance is measured in geology, pressure, safety, and cooperation. This is where tunnel engineering meets the boundary between continents, and where a line on a map must become a system capable of surviving beneath the sea.